Hello guys, welcome to 4.8. We're looking at a specific type of function called the surge function and a drug concentration or a substance concentration inside our body after consuming stuff. All right, so the example that we're looking at first is nicotine in blood. All right, so we start with someone smokes a cigarette, and then the nicotine in concentration in the blood, you can see that at time 0 is 4, and then as time increases, the nicotine in the blood will increase dramatically, and then so increase really fast and then decrease slowly. Right, decrease slowly. Right, now in the graph we can see that a sudden increase in the nicotine in your blood increase very fast in the first 5 to 10 minutes, right? And then after that it gradually decreases down because as nicotine gets uh, consumed by our body, and then there is less nicotine in our concentration in our body. Now, these type of function where it increases suddenly and then decrease down slowly, it's called um, a surge function, right? So this would be an example of the surge function, right? And it can be used to model a different type of consumption of drugs. Like for example, you're taking a painkiller, right? How what's the concentration of the chemical in your body, right? So today we're going to look at this type of function, and let's start with the general form. All right, so we have the surge function that has the form of y is equal to a times t times e to the power of negative bt, right? For positive constants a and b, right? And these type of functions increases rapidly and then decrease towards 0 at a maximum time of t equal to 1 over b, right? So you can see that it actually reaches the peak at time 1 over b, right? So the peak means when the your body has the highest concentration of the substance. Right. For example, our earlier example at here, we see that 10 minutes after someone has a cigarette, the nicotine in the level rate rose to 17. Right. So in that case, this will be our peak, right? Approximately there, because we don't actually have a really nice timetable to know a smooth curve to know exactly where the peak is, but this is a fairly good approximation of we can see the peak and then slowly decreases. All right, so um, one question is, of course, with different drugs, different chemicals in your body, the level of um, the chemicals entering your body and leaves the body might be different, right? So that's what A and B, the constants, are going to um, it's going to make. We can look at variations of the function, and let's see what the parameter A and B does to our function. All right, so here we are letting A be equal to 1, and then we're looking at different values of B. So we can see that in this graph, for different positive values of B, the general shape of the curve does not change, right? We all see them increase fast and then drop down slowly. But as B decreases, the value of B decreases, the curve rises for a longer period of time and to a higher value, right? So for the smallest B value, we can see that it increases for the longest time and then hit the peak and then drop down slowly. Whereas for large B values, it shoots up very fast and hits the peak also faster than the other three, and then drops down slowly. All right, so let's look at another variation of this. All right, so here we pick some specific values for B, B equal to 1, 2, and 3. So we can see that we remember that the peak happens at time equal to 1 over B, right? So when B is small, that means it's going to take longer for the function to hit the peak, right? So in this case, t is 1/1, which is 1, right? When b is 2, it's going to hit the peak faster, which is 1/2. But you can see that it hits the peak faster, but it's not as high as the previous one, and so on. When b is equal to 3, it hits the peak even faster, 1/3, right? And then again, we can see the sort of shape when the b value is smaller, it increases for longer and has higher value. When b is large, then the function is going to increase for shorter, but hits the peak faster. All right, so here is a quick example of application. Right, so here we're looking at two different types of patient taking paracetamol or with pro propanthenol. I'm really bad at pronouncing these medical terms, but from my research in Google, I think paracetamol or acetaminophen. They are like Tylenols, like painkillers. All right. So anyway, for those of you who are interested in the medical field or thinking about going into bio or chemistry, you might know this much better than me. All right. But what we're going to look here is just how does the concentration effect in people with normal patients or patients with slow absorption. All right, so let's look at the first one. So if the normal patient just take paracetamol alone, then you can see that it's normal. Okay, it increases fairly fast. Within 1.5 to 2 hours, it's going to reach the highest concentration, the peak, which is about here. All right. But if they take paracetamol with propanthenol, then it's going to hit the peak a little slower, probably about here, right? So you can see that it increases much slowly than taking paracetamol alone. But for people who have slow absorption, if you just look at the solid blue line, if they take paracetamol alone, and it actually takes it a little longer for them to hit the peak, and then the peak is not as high as a normal patient taking paracetamol alone. But for people with slow absorption, if they take paracetamol and metoclopramide, I have no idea, it actually speeds up their absorption and then reaches higher peak than taking paracetamol alone. So in this case, we can think about having different types of patients and taking medications alone with or without some sort of catalyst to speed up the time, as to speed up their bodies to absorb these type of chemicals. Right, so by looking at this, we can help doctors and researchers building these kind of tables, and they can uh, draw to different conclusion on how to better improve these type of treatments and to save money and then cure people faster. Right. All right, next we're looking at the minimum effective concentration. So basically, it just means what's the concentration of the drug that's necessary for for that drug to achieve a pharmacological response. So how much do you need to take, and what's the time needed in order for the medication to work? Right, the time at which this concentration is reached is referred to as onset. Uh, Termination occurs when the drug concentration falls within this level. All right, so we can look at the graph, kind of pretty self-explanatory, right? The first part, right, this little part is onset, right? And then duration of effectiveness is when the level of concentration is over the minimum effective concentration, right? So it's effective between this timeline, right? Of course, includes the peak, right? And termination is when um, the concentration falls below the minimum effective concentration, right? So it's just some of the technical term to describe this graph. Now, I don't expect everyone to understand like what the terms are meaning, but if I were to give you this graph, then I want you to be able to, you know, say something about this graph. Okay, if it falls below the minimum effective concentration, what does that mean? What does it mean to be above the minimum effective concentration, and so on. All right, our next example is not so much about math or calculation, but a little more about looking at the graphs. Okay, so example 3, Depo-Provera was approved for use in the US in 1992 as a contraceptive. So in this figure, it shows the drug concentration curve for a dose of 150 milligram given intramuscularly. The minimum effective concentration is about 4 nanogram per milliliter. How often should the drug be administered? All right, so we can see that the horizontal axis, that's T in months. All right, so after the drug is being taken, it goes up to the peak in about half a month, right? Less than a month, and then slowly decrease down over time, right? Throughout the months, right? So we know that the minimum effective concentration is about 4. So that would be about right here, right? 4. Maybe a little higher, 4, like that, right? So our goal is to keep the concentration above 4 in order for the drug to be effective, right? So we actually have another nicer graph that they give us where 4 is the minimum effective concentration line, right? So we can see that the minimum effective concentration line after taking the medicine or taking the drug actually hits the line when it's about 4 months, right? Around 4 months, right? So if we take the drug at time 0, and after about 4 months, the concentration of the drug in your body is going to be lower than the minimum effective concentration, right? So when should the next dose be administered, right? So we can say probably about 4 months, right? Because after 4 months, and then you take the drug, and then we can kind of reset the surge function, right? Maybe it's gonna go up again, right? Go up again, and then slowly come down, and then maybe in another 4 months, it's going to drop down to the over the minimum effective concentration, and then you do that again, right? So that's what we can use, right, for doctors to help us in different medical fields. How long or how often should we take our medication? All right. So uh, not much complicated things from this section, but mostly we're just working with the function, right? The search function, this form, right? And knowing how to read the graphs, understanding peak, right? How to find peak. Peak is 1 over b. T is equal to 1 over b, right? And the minimum effective concentration, what does that mean, right? It means we want the concentration in our blood be over that line in order for the medication to be effective. All right. So that's it for 4.8, and I'll see you next time.